Okay, in today's lesson, we're going to look at how to find infinite limits and how to find limits at infinity. So what's the difference in between these? Infinite limits is if you have a limit as x goes to some number of a function and it's equal to positive or negative infinity. That's what we call infinite limits. Your limit is going to infinity or negative infinity. Limits at infinity, on the other hand, is when you are doing a problem in which you have the limit as x goes to plus or minus infinity of a function. And this could either be equal to L, or it could also be limits at infinity could also be infinite limits and equal to a plus or minus infinity, either positive infinity or negative infinity. Okay, and so look at these two main types. What's cool is if you have a limit as x approaches a constant, a number of f of x, and it's equal to infinity or negative infinity, what you're going to have here is a vertical asymptote. On your graph of the function. Okay. Now, if you happen to have the limit as x goes to infinity or the limit as x goes to negative infinity, f of x is equal to a constant value. This is telling you as your x gets extremely large or extremely small, it's going to a constant value. So you have a horizontal asymptote. And then if you have a limit as x goes to infinity or negative infinity, approaching infinity or negative infinity, so you have a limit at infinity going to infinity, here you're going to have a slant or oblique asymptote. So graphically, infinite limits and limits at infinity tell us about the asymptotes of our function. And that's going to come in play in mainly our third unit, but kind of introducing this topic now. So here you can see the goals that we're going to do today. It's quite lengthy. So our first goal is we're going to start with infinite limits. So again, when I was talking about infinite limits, remember this is the limit as x goes to c of f of x, and that's equal to infinity, or the limit as x goes to c of f of x will equal negative infinity, and that makes it an infinite limit. So in words, if the function f of x approaches infinity or negative infinity as x approaches a from the left or from the right, so one-sided limits work just fine, then the graph x equals c has a vertical asymptote of the graph of the function f. Okay, so infinite limits relate to vertical asymptotes of our function graph. How do we find our infinite limits? All right, so the easiest process to go through is determine all x values, and usually the most common function that you'll see vertical asymptotes are of the functions that you've learned up to now is rational functions. So we're going to use this a lot when we're talking about rational functions. So determine all x values for which the denominator of the rational function equals 0. So set the bottom equal to 0 and get those values. Then you're going to evaluate the numerator at the x value found when the denominator equals 0. Okay, and then you'll have a certain cases that occur. If the numerator also equals 0 when evaluated at the x value in which the bottom equals 0, you have the indeterminate form. So that means the numerator and denominator 0. Okay, and so we must do some algebraic technique up to the function to bring this down. Most commonly is subtracting. Sometimes you'll have to do some other trig identities and things like that to work with. And then if you're successful, this means that the graph does not have a vertical asymptote. So if you can cancel out the term that's giving you that 0, that if you can cancel out terms from the top and the bottom, and that happens to have the term with the x value of where the denominator equals 0 gets canceled out, then you're no longer going to have a vertical asymptote. This is an example where you're going to have something called point or removable discontinuity. I ran out of room there. Discontinuity. So it's not a vertical asymptote in this place. If the numerator is not 0, okay, then you have a vertical asymptote in your graph. At that x value in which the denominator equals 0. So let's see this work. Find the vertical asymptotes, if any, of the graph of the function. So step 1, I take the denominator and set it equal to 0. All right, we're going to solve this for x. And when you take the square root of each side, you got to use plus or minus. Square root of 4 is 2. So I have two possibilities. X is 2 or x equals negative 2 could be vertical asymptotes. To figure out they are, okay, so this, I dealt with the denominator. So now I'm going to look at the numerator. And in the numerator, which is x squared, and we replace every x with the value I found in step 1. So that's going to become positive 2 squared, which gives me a 4, and negative 2 squared, which also gives me a 4. I look at this and say, okay, is this number 4 0 or not 0? It is not equal to 0. So my conclusion is I have a vertical asymptote at both x equals 2 and x equals negative 2. Because the denominator was equal to 0 at 2 and negative 2, but when I evaluate the numerator at those two values, I did not get 0. Okay. Now for this next one, again, we're going to start with our denominator. That's x cubed minus 5x squared plus x minus 5. I'm going to do factoring by grouping here. So x squared comes out of the first two terms. That leaves me with x minus 5. Nothing comes out of this first term, so I'm going to multiply by 1, x minus 5. So I got x squared plus 1. Well, let's write it this way. So in these two terms, x plus minus 5 is our GCF, so it leaves me with x squared plus 1. It really doesn't matter which way you write it. So I need to set that equal to 0. So x minus 5 equals 0, or x squared plus 1 will equal 0. So x equals 5. Or x squared equals negative 1. X is equal to plus or minus square root of negative 1. Well, square root of negative 1 is I, which is not a real number, and by definition, our answers have to be real numbers, so this one gets thrown out. So x equals 5 is our only possibility for a vertical asymptote. So now we go to our numerator, which is x squared minus 2x minus 15, and replace every x with 5. And solve this, so we got 25 minus 10, so that's negative 20, that's 25 minus 25, which is 0. So this time, when our denominator equals 0 at 5, we evaluate that, our numerator also equals 0. So we have that indeterminate form. So we have to make sure, we have to see, do I have a vertical asymptote there, or do I have a removable discontinuity at that point? So to do that, we're going to do the limit as x goes to 5, because that's what we're focusing on, is this x value of 5 of our function here. And we're going to see what we get when we evaluate this. Alright, so I'm going to use my factoring technique, because if I do direct substitution in here, I get 25 minus 10 minus 5, which we already know is 0. And then that's 0 on the bottom as well. So direct substitution gives us 0 over 0. So we're going to try factoring the top. That's going to factor x minus 5 and x plus 3. And the denominator, when we solved it, we already factored it up here. So that's x minus 5, x squared plus 1. And so the x minus 5 term canceled out. So I've removed the term that has the equal to the 0. This term here that gives us our 0 has been removed out. So this tells us we have no vertical asymptote. We have a point discontinuity at x equals x equals 5. So that's an example with no vertical asymptote. Okay, now dealing with infinite limits, we have a few properties that we can learn, and it kind of makes sense. So here, c and l are real numbers. Function f and g are defined such that the limit as x approaches c of f of x is infinity, and the limit as x approaches c of g of x is some number, l, some real number. So if I take the limit as x approaches c of f of x plus g of x, or f of x minus g of x, using our properties that we learned earlier in this unit, that would be the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And so that's going to be infinity plus L. Well, infinity plus some other number is still infinity. Okay, so that's going to give us our limit is going to be infinity there. Okay, and then for the limit as x approaches c of f of x times g of x, so that's going to be infinity times L, well, infinity, and let's assume L is a positive number. So infinity times positive, so infinity times 2 is double infinity, which is just infinity. We don't have double, triple infinity, okay? Now, here was what if L is a negative number? Well, then we're going to have infinity times a negative 2. So that's going to give us negative infinity. So the infinity sign switches. On the next one, here we're going to have the limit as x approaches c of that's wrong. That should be g of x over f of x. Okay. Let me write that a little clearer. Okay, this should be our g of x, this should be our f of x. Okay, so if we have the limit as x approaches c of g of x over f of x, we have a constant over infinity. So, well, think about that. If my constant, let's say our constant, let's say L is 1. Okay, and if I had 1 over 10, and then 1 over 100, 1 over 1,000, so as my denominator is getting larger and larger, what is my function approaching? It's approaching 0. So that limit approaches 0. At the top is staying the same, the bottom's getting larger and larger. These properties, these three properties here, apply to one-sided limits. So it doesn't matter, it doesn't have to be two-sided limit, it can be a one-sided limit. Also approaches if the limit as x approaches c of f of x is equal to negative infinity, not just infinity. So all the same rules apply. These signs would just be switched from infinity to negative infinity. But all of it is the same. So the rules apply in all those cases of any types of infinite limits. Okay. So let's look at how we can apply this and what we can do to find. So we're asked to just to find the one-sided limit here. The limit is x approaches 1 from the left of x squared minus 3x and x minus 1. So first thing we want to do is we're going to see if we have a vertical asymptote or not. So we kind of put all this information together. So I'm going to start by looking at my denominator. That's x minus 1, set that equal to 0, I'll get x equals 1. And switch to my numerator. And we have x squared minus 3x, so it becomes 1 squared minus 3 times 1. So that's 1 minus 3, which is a negative 2. So that's not 0, so therefore I know I have a vertical asymptote at x equals 1. Okay? So now that we know that we have a vertical asymptote here at x equals 1, if it's, just think about your graph. If you know you have a vertical asymptote going on at x equals 1 here, the only possibilities for my function is I can be approaching infinity from going to like this, approaching that vertical asymptote in that direction, or it could be approaching like this. So we can go, so our only options here is our answer is going to be infinity or negative infinity, but we got to figure out which one of those it's going to be. And to figure out which one it's going to be, all we do is what's called some test values. So we want to evaluate the limit at some test values. Okay, and we're going to pick values of x that are close to 1, but since we're looking at our left-handed limit here, we want something a little less than 1. So let's say I decide to try the limit as x approaches 0. So try direct substitution first. I get 0. Well, that doesn't help me decide if it's positive or negative infinity. So let's try something a little bit closer to positive 1. So we're going to do as x approaches 1/2. So limit as x approaches 1/2 of our function. And again, we're going to start by try direct substitution. All right, so that's 1/4 minus 3/2 over a negative 1/2. All right, so 1/4, so let's get a common denominator. Now it's going to be 6/4 negative 1/2, so that's negative 5/4 divided by negative 1/2. So that's negative 5/4 times a negative 2 over 1, which is positive 10/4 or 5/2, which is a positive number. So I went from 0 going toward positive, so that tells me I'm getting larger and larger. So my conclusion, therefore, is the limit as x goes to 1 from the left of this function is going to infinity. So we know we're going to infinity. So it's a little bit harder when it has vertical asymptote, because we know the only answers are going to be infinity or negative infinity. And we just had to figure out which one it is. All right, now let's try this next one here. So we're trying to find the limit as x approaches 0 from the right of 6 minus 1 over x squared. All right, so I'm going to break this up using my properties of limits. There's a couple ways you can approach this problem. I'm going to break that up. Now the limit as x approaches 0 of 6 of any constant, whether if it's left side limit, right side limit. Remember, the limit of any constant is 6. So that one's easy to figure out. This one's a little bit harder because we have a rational function. So again, I'm going to look for my vertical, if I have a vertical asymptote or not. So I'm going to check my denominator. And I'm going to set it equal to 0. So x must be 0. And then I'm going to plug that into my numerator. Well, my numerator is just 1. I don't have anywhere to plug in 0 in there. That's okay. My numerator is not equal to 0. So I do have a vertical asymptote. So here's an example where we do have a vertical asymptote at x equals 0. So we know this limit here is going to either be infinity or negative infinity. We've got to figure out which one. So we're going to do a test point. I want a little bit greater than 1. I mean, a little greater than 0. So I'm going to test the limit as x goes to 1/2 of 1 over x cubed. Okay, trying direct substitution in. That's 1/2 cubed, which is 1/8. 1 flip and multiply, I get 8. So I'm going towards a positive direction, so that means this has to be infinity. But my entire limit I'm looking for is this 6 minus infinity. Well, 6 minus infinity is going to be negative infinity. So the limit as x goes to 0 from the right hand side of 6 minus 1 over x cubed is negative infinity. So we kind of put the different things together. Now that we've learned about infinite limits, let's talk about limits at infinity. Remember, limits at infinity is where we have the limit as x goes to infinity of a function, or the limit as x goes to negative infinity of a function. And that's what a limits at infinity is. Physically, limits at infinity describe the end behaviors of the function. And if those end behaviors happen to equal a constant, we could be, if the limit as x goes to positive or negative infinity equals a constant, it also describes horizontal asymptotes. Okay, so it describes what's happening at the ends of our graphs, that's the end behaviors, and then it also describes our horizontal asymptotes if the limits happen to be constants. So let's look at this graphically, how we can figure this out. So for A here, I'm finding the limit as x approaches negative infinity. So if I'm going, my x is getting extremely smaller and smaller, so I'm going in this direction. And I notice that my graph is getting closer and closer to this horizontal asymptote here at 2. So that means my limit as x approaches negative infinity of f of x has to be 2. Here on the right-hand side, to do part B, the limit as x approaches infinity, I notice that my graph is also approaching the horizontal asymptote of 2. So that means that answer is 2. On my h of x function here, as x goes to negative infinity, my graph is getting closer and closer to a height of 2. But as x approaches infinity, my graph is getting closer and closer to a height of 4. So we might not have the same answers there. Note, if the limit as x goes to negative infinity f of x equals a constant, a real number, or the limit as x goes to infinity of that equals a constant or a real number, then the graph has horizontal asymptotes at y equals that L value, is the equation of that horizontal asymptote. There are two main techniques to find the limits at infinity of rational functions. So we're going to focus on rational functions, and then last thing we're going to do is if it's a polynomial. And those are the two that we're going to focus on here today. So the first technique is called the dividing out method, or the dividing method. Now this one says, okay, you look at your rational function, you find your x, you find the highest degree of any x in the problem. Okay, and then you divide every term by the highest degree of in the problem. Okay, then you simplify each of those terms and you evaluate each term as x goes to infinity or negative infinity, whichever one you're looking at, and then that'll give you your answer. So let me show this in a problem so you can kind of see how it works out. So I'm doing the limit as x goes to negative infinity of 3x squared minus 2 plus 5x to the fourth plus x plus 4. So x to the fourth tells us that the degree 4 is our highest degree in this problem. So I'm going to do the limit as x goes to negative infinity. And then in the numerator here, I'm going to take that 3x squared and divide it by x to the fourth. Minus 2 divided by x to the fourth. And then denominator, we'll do the same thing to each term. 5x to the fourth divided by x to the fourth. Plus x divided by x to the fourth. Plus 4 divided by x to the fourth. So you divide each term by the highest power. Okay. I haven't evaluated the limit yet, so that's the reason I have to keep writing my limit notation. Then I'm going to simplify each fraction here. So this first fraction becomes 3 divided by x squared. Second fraction does not simplify down. Third fraction, first fraction, the denominator is 5. 1x cancels out. And this one does not simplify. Oh, that should be a 2. The x canceled out. The 1 stayed. Okay. Now, I'm going to actually do my limit. So limit as x goes to negative infinity of 3 over x squared. Well, remember, if the bottom is going to infinity, so the limit of x squared is just negative infinity squared is infinity. So 3 over infinity, that's going towards 0. And then 2 over infinity, that's going towards 0. We got 5 plus 1 over infinity, that's going to 0. Well, 1 over negative infinity, that's going towards 0. And then 4 over infinity there, that's going towards 0. So I'm left with 0 over 5, which is 0. So the limit of this problem using dividing out method is 0. All right. Next problem on B here, our highest degree is 2 because these are tied. So our highest degree is 2, so I'm going to divide out every term by x squared. I do need to see this step in your work. I know you could probably skip to the simplifying, but I need to show this because this shows me which method you're using. So please make sure you write all of this step on your work. Pretty much what work I'm showing is what work you need to be kind of showing as a minimum. All right, and so here on the first term, the x squares cancel out, just leaves us with a 2. This term is already simplified. Denominators, the x squares cancel out, leaves us a 3. 1x cancels out, and this one is already simplified. The limit as x goes to infinity of 2 is just 2. Limit of a constant is that constant. And then the limit as x goes to infinity of 6 over x squared, that's 6 over infinity, which we've already known to be 0. Limit as x goes to infinity of 3 is 3. The limit as x goes to infinity of 4 over infinity is 0. And the limit as x goes to infinity of 1 over x squared, so that's 1 over infinity, which is also 0. So our answer is going to be 2/3. That's what our limit is equal to. All right. Let's try this next one. We'll do a limit as x goes to negative infinity of this function. Our highest degree is x squared. So I'm going to divide every term by x squared. So that's 2x squared over x squared minus 3x over x squared plus 5 over x squared, x over x squared minus 2 over x squared. Let's just move it this way. Limit as x goes to negative infinity. X squared simplified down gives us 2. X cancels out, gives us 3 over x. This one's already simplified. X's cancel out, leaves us 1 over x. And this one's already simplified. So let's see, the limit as, well no, we are ready to evaluate, so we don't need limit notation. Limit as x goes to negative infinity of 2, limit of a constant is that constant. Okay, limit as x goes to negative infinity, that's 0, so minus 0. And then limit as x goes to negative infinity of 5 over x squared is plus 0. Limit as x goes to infinity of 1 over x is 0. And limit as x goes to infinity of 2 over x squared is 0. So I end up with 2 over 0. Now remember, 2 over 0 does not exist. But because we know that we're going to have some sort of slant asymptote in this case, we need to figure out, is this does not exist? Is it approaching a certain value? Say, is it going toward infinity or is it going toward negative infinity? So I need to figure out which one is my actual answer here. As x gets extremely larger, is it since it's not approaching a single value, it has to be approaching either infinity or negative infinity. So to figure out which one it is, we're going to go back to our original problem. So remember, we have the limit as x goes to negative infinity of 2x squared minus 3x plus 5 over x minus 2. Now, we're going to try, it's sort of, think of this like direct substitution, because technically we never reach infinity, so we can't actually plug it in. But we're going to pretend that we can plug in infinity, in this case negative infinity. And we're going to see what's happening. If we can describe what's happening to our function, we can figure out if we're going to infinity or negative infinity. So if I take negative infinity and I square it, that gives me a positive infinity. Times 2 is still positive infinity, so that's an infinity. Negative 3 times a negative infinity gives me a positive infinity, and then plus 5. All right, infinity plus another infinity plus 5 is just infinity. Negative infinity minus 2 is still negative infinity. So a positive infinity divided by negative, positive divided by negative is negative. So we're going toward, so this does not exist. We need to describe it a little bit better. So now we can say that this is approaching negative infinity as our solution. So that's the dividing out method. Now let's look at our next method, which actually takes longer to explain than actually the work. The work on this one is very, very quick, but kind of know the rules and memorize the techniques. This is just a shortcut as the dividing out method. Because you notice I had to show a lot of work on this. Here is a shortcut where you don't have to divide it out as much. So if you want to find the limits to infinity of rational functions algebraically, we can use a method called the n-behavior model. I did red for a while. Let's choose colors. And we'll abbreviate that. You can just do EB, n-behavior model. So for the NVA model, first thing you have to do is identify the degree, which I'm going to call n, of the numerator. So the degree of the numerator I'm going to evaluate with the variable n, and the degree of the denominator, which I'm going to evaluate with a d. So the highest power of the numerator is your degree of the numerator, highest power of your denominator is the degree of your denominator. Now, looking at n and d, you have the method BOBO, bigger on bottom, 0. Bigger on bottom, 0. That's what that stands for, bigger on bottom, 0. That is, if the degree of the numerator is more than the degree of the denominator, so if denominator is greater than numerator. So the bottom has the bigger power. Then, bigger on bottom, your answer to the limit problem is 0. The rational function limit as x goes to infinity or negative infinity is 0. No work needed. Okay, next one is bottom equals top coefficients, which we call BETC, is what we would write to show that we're using this technique. So if the degree of the numerator equals the degree of the denominator, so if d equals n, the limit is the ratio of the coefficients that have the highest degree. So ratio of the coefficients of the highest degree. And then we have to do sort of like we did in that last problem, plug in infinity if we're doing limit as x goes to infinity, or plug in negative infinity if we're doing limit as x goes to infinity, to figure out if our coefficients should be positive or negative. And that's what I mean by check your signs. And then the last possibility is bigger on top, undefined. Bigger on top, undefined. BOTU. Bigger on top, undefined. If the degree of the numerator is greater than the degree of the denominator, so n is greater than d, the limit does not exist. But just like in that last problem, you can't just stop with d and e. You must state rather which direction it does not exist in. So you have to figure out if it's going to infinity or if it's going to negative infinity. And you do that by just substituting in like I just did in the last problem. So those are our 3 possibilities. So how do we work something like this? So for A here, we got the limit as x approaches negative infinity. My numerator is a quadratic. It has degree 2. My denominator is a cubic. It has degree 3. So I know my numerator's degree is 2. My denominator's degree is 3. So I notice that 3 denominator is greater than. Okay, so I notice that my denominator is greater than my numerator. So bigger on bottom is 0. Answer 0. That's it. That's all the work you have to show. Now, for D, don't fall in the trap. I put this B here, I put this on here because you would see, okay, you see this x squared and you think, okay, this is degree 2, but it is not degree 2 because what you're looking at here is this is the square root of 2x squared, which is the square root of 2x. When I take that square root of a square, it's just x. So this, because it's inside the square root, we kind of need to simplify it down a little bit and rewrite it as, and we only care about this end behavior model here. We're only looking at the leading term. So I don't care about any of the other terms here. So when I'm doing this as end behavior model, I can rewrite this equation as square root of 2x over 4x. So my numerator's degree is 1, my denominator's degree is 1. I got numerator is equal to denominator, bottom equals top, coefficient is what I'm going to do. So the coefficient of the top is square root of 2, coefficient of the bottom is 4. So that tells us that it's going to be the square root of 2 over 4. But I have to remember to check my signs. Is this going to be positive the square root of 2 over 4 or negative the square root of 2 over 4? To do that, I go back to my original problem, limit as x goes to negative infinity, the square root of 2x squared plus 1 over 4x plus 2. And I'm just going to plug in my negative infinity. And I'm not really caring about what it is, just if it's going to be positive or negative. So negative infinity squared becomes positive, times 2 plus 1 is still infinity, square root of infinity is still infinity. So I got infinity going on here. And 4 times a negative infinity is negative infinity, plus 2 is still negative infinity. So positive divided by negative is negative. So my answer is negative the square root of 2 over 4 for that method. All right, let's try one more here. The limit as x goes to infinity of this function. So first thing I noticed, the numerator's degree is 2, the denominator's degree is 1. So numerator is equal to 2, denominator is equal to 1. So I have the numerator is greater than the denominator. And so bigger on top is undefined. So I know I'm going to have, using my end behavior model, I'm going to have either infinity or negative infinity. So to figure out which one that is, I'm going straight to substituting in infinity into the original problem and seeing if I can get a positive or a negative answer. Infinity squared times 2 is still infinity, minus infinity. Oh, infinity minus infinity. How do we figure that out? Well, this is infinity squared, so that's a lot bigger number minus a smaller infinity. That's the reason why this doesn't work out directly. Substitution is the reason why you can't solve these by direct substitution. We'll just think, so we have a humongous infinity and we're subtracting a little infinity from it. We're still positive, plus 5, so we're still positive on the top here. And then infinity minus 2, we're still positive here. So positive infinity divided by positive infinity is positive infinity. So our limit is going to infinity. All right, last thing we're going to learn is called the end behavior model if we're looking at polynomial functions. And this end behaviors, again, remember to find end behaviors, that's the limit as x goes to a positive or negative infinity of our polynomial function here. And so we're going to use this technique here. First, you got to find the degree of the polynomial and the value of the leading coefficient. So the degree of the polynomial and the leading coefficient. If you can determine those two things, that will tell you how you do it. So if the degree is even, 2, 4, 6, 8, etc., the end behaviors will go in the same direction. If the degree is odd, the end behaviors will be in different directions. So we have 4 cases can go on. If the degree is even and the leading coefficient is positive, this polynomial will have a graph that follows sort of like y equals x squared, because y equals x squared is the simplest polynomial that has an even degree and a positive leading coefficient. And we know that this graph looks like this. And so we know this left end will be going to infinity and the right end will be going to infinity. So we translate that to say the limit as x goes to negative infinity, that's the left hand end behavior, that's going up, and the limit as x goes to infinity is also going up. So that's how we would describe our end behaviors. Now if the degree is even but the leading coefficient is negative, what I do is I think about the simplest even a polynomial with a negative coefficient, and that's negative x squared. And we know that's just flips across the x-axis and it looks like this. So our end behaviors are going in these two directions. So the limit as x goes to negative infinity is negative infinity, and the limit as x goes to infinity is also negative infinity. So notice they are the same answer. Both negative infinity for case 2 and both positive infinity for case 1 because our degree was even. They're going to be the same. All right, now what if our degree is odd and our leading coefficient is positive? Well, think about the simplest odd polynomial that has a positive leading coefficient, and that would be y equals x cubed. And we know from college algebra that graph looks like this. So our graph of this would be from the left end will be going down and the right end will be going up. So the limit as x goes to negative infinity of f of x will be negative infinity, and going up here the limit as x goes to infinity of f of x will be infinity. And the last one, if the degree is odd and the leading coefficient is negative. The simplest odd and negative would be negative x cubed, and that flips over the x-axis again, so it looks like this. So the left end is going up, the right end is going down. So limit as x goes to negative infinity of f of x is infinity. The limit as x goes to infinity of f of x is negative infinity. So notice in case 3, it's odd, so my answers are different directions. One's negative infinity, one's positive. Same in case 4. One's positive infinity, one's negative infinity. All right, so I need to find the limit as x goes to negative infinity and limit as x goes to infinity of f of x for the following polynomials. And so what I do is I look at my degree. And my degree of this one is 2. My leading coefficient is 4. So I have an even polynomial with positive leading coefficient. So even, they're going to go in the same direction. Positive, they're both going up. So that's the shape. So my answer is going to be the limit as x goes to negative infinity of f of x, which is describing this arrow here. That's going up, so that's equal to infinity. And the limit as x goes to infinity of f of x, that's describing this side, which is also going up, so it's going to be infinity. Okay, you do not have to show this work here. I just specified here. Everything else is all you really have to show, and that's what I'm going to show in the next one. All right, so negative 4x cubed plus 6x minus 11, I have a degree 3, so that's an odd degree, and a leading coefficient of negative 4, so that's negative. Okay, so degree of odd means they're going in opposite direction. And since it's negative, that means we end at the negative direction. So we're going to start up and then go down, like negative x cubed. And so my answer is going to be the limit as x goes to negative infinity of f of x. And that's describing the left end behavior. And so that's going up. So that'd be positive infinity. And the limit as x goes to infinity of f of x is describing my right end behavior. And that's arrows going down. So my answer is negative infinity. All right, f of x is equal to x minus 2. So my degree is 1, which is an odd degree. And my leading coefficient is 1, which is positive. And so odd, opposite direction, positive. We're going to end at the positive side. So we got to start negative. And then, so that gives us the limit as x goes to negative infinity of f of x, left end behavior, that's going down, so that's negative infinity. And the limit as x goes to infinity of f of x is my right end behavior, arrows going up, so that's infinity. All right, here we have f of x is equal to 4x cubed minus 9x to the 6th minus 11x plus 12 minus 4x to the square. So my leading term there is that negative 9x to the 6th. And so it is an even degree and a negative leading coefficient. And so even, same direction. Negative means they're both going down. So my limit as x goes to negative infinity of this function will be negative infinity, going down from the left side. The limit as x goes to infinity, the right end behavior of my function is also going down. And that's how you find the limits at infinity of polynomials.